Section 3.7, Limiting Reactants. Suppose you wish to make several sandwiches using 1 slice of cheese and 2 slices of bread for each. Using BD as bread and CH as cheese and BD2CH as a sandwich, the recipe for making a sandwich can be represented like a chemical equation. 2BD plus CH yields BD2CH. If you have 10 slices of bread and 7 slices of cheese, you can only make 5 sandwiches and will have 2 slices of cheese left over. The amount of bread available limits the number of sandwiches. An analogous situation occurs in a chemical reaction in which one reactant is used up before the others. The reaction stops as soon as any reactant is totally consumed, leaving the excess reactants as leftovers. Suppose, for example, that we have a mixture of 10 moles of hydrogen and 7 moles of oxygen and wish to form water. The balanced equation is 2 moles of water plus 1 mole of oxygen yields 2 moles of water. Because 2 moles of hydrogen is stoichiometrically equivalent to 1 mole of oxygen, the number of moles of oxygen needed to react with all the hydrogen is 10 moles of hydrogen at 2 moles of hydrogen per 1 mole of oxygen is 5 moles of oxygen. Because 7 moles of oxygen is available at the start of the reaction, 7 moles of oxygen minus 5, there's 2 moles of oxygen present when all the hydrogen is consumed. The reactant that's completely consumed in the reaction is called the limiting reactant because it determines or limits the amount of product formed. The other reactants are sometimes called excess reactants. In our example shown in figure 317, hydrogen is the limiting reactant, which means that once all the hydrogen has been consumed, the reaction stops. The excess reactant is O2, and some is left over when the reaction stops. There are no restrictions on the starting amounts and reactants of any reaction. Indeed, many reactions are carried out using an excess of one reactant. The quantities of reactants consumed and the products formed, however, are restricted by the quantity of the limiting reactant. For example, when a combustion reaction takes place in the open air, oxygen is plentiful and is therefore the excess reactant. If you run out of gasoline while driving, the car stops because the gasoline is the limiting reactant in the combustion reaction that moves the car. Before we leave the example illustrated in 317, let's summarize the data. The initial quantities of hydrogen was 10 moles. The initial quantity of oxygen was 7 moles, and of water was 0 moles. When it changed during the change of the reaction, you lost all 10 moles of hydrogen, you lost 5 moles of oxygen, and you ended up with 10 moles of water. The final quantities, you had no hydrogen left over, you had 2 moles of water left over, and you had 10 moles of oxygen left over, and you had 10 moles of water produced. Figure 3.17, limiting reactant. Because hydrogen is completely consumed, it's the limiting reactant. Because some oxygen is left over at the reaction is complete, oxygen is the excess reactant. The amount of water formed depends on the amount of limiting reactant, hydrogen in this case. The second line of the table summarizes the amounts of reactants consumed, where the consumption is indicated by the minus sign, and the amount of products formed indicated by the plus sign. These quantities are restricted by the quantities of the limiting reactant and depend on the coefficients in the balanced equation. The mole ratio of hydrogen to oxygen to water is 10 to 5 to 10, conforms to the ratio of the coefficients in the balanced equation, 2 to 1 to 2. The final quantities, which depend on the initial quantities and their changes, are found by adding the initial quantity and the change quantity for each column. None of the limiting reactant, hydrogen, remains at the end of the reaction. What remains is 2 moles of excess reactant and 10 moles of product. Theoretical yields. The quantity of product calculated to form when all the limiting reactant is consumed is called the theoretical yield. The amount of product actually obtained, called the actual yield, is almost always less and can never be greater than theoretical yield. There are many reasons for this difference. Part of the reactants may not react, for example, or may react in a different way than desired. These are called side reactions. In addition, it's not always possible to recover all the product from the reaction mixture. The percent yield of the reaction relates actual and theoretical yield. The percent yield is the actual yield divided by the theoretical yield times 100%.